Welcome to week 10, the final week of Fundamental of Python and Machine Learning. In chapter 12, we will study how a trained machine learning model can be made available to another application. Building a model inside a notebook is only one part of the process. For the model to support a real workflow, another program must be able to send it new feature values and receive a prediction. In this lesson, we will review a complete deployment example using a saved model, a Flask REST API, a command line test, and a simple Python client. We will also connect the individual deployment steps into one complete end-to-end workflow. By the end of this chapter, you should be able to explain what model deployment means and distinguish model training from inference. You should understand how a REST API allows different applications to communicate with a prediction model. You will review how to clean data, select features, compare algorithms, and train a final pipeline. You will learn how a trusted model artifact can be saved and loaded, how Flask can expose a post endpoint, how JSON input can be validated, and how a prediction can be returned as JSON. You will also learn how to test the service with curl and how to create a small Python client using the request library. Finally, you should recognize that a classroom demonstration is not automatically a secure, reliable, or production-ready application. Before discussing deployment, let's review how the course has progressed. We began with Python and machine learning foundations. We used NumPy for numerical arrays, pandas for tabular data, and matplotlib for visualization. We then learned the Scikit-learn workflow and studied linear regression, logistic regression, k-nearest neighbors, and k-means clustering. Each chapter added another part of the complete machine learning process. Deployment does not replace those earlier steps. It depends on them. A deployed model is useful only when its data preparation, evaluation, interpretation, and limitations have been handled responsibly. Model deployment means making a trained model available for practical use. During development, the model may exist only inside a notebook or Python process. Deployment creates a repeatable way for another user or system to provide new feature values and obtain a prediction. The consumer should not need to understand how the algorithm was trained. It only needs to understand the required inputs, the available endpoint, and the format of the response. Deployment therefore connects machine learning with software engineering. Training and inference are different stages. Training uses historical data to learn the model's behavior. It may include cleaning, scaling, feature selection, cross-validation, tuning, and evaluation. Inference occurs after training. During inference, the saved model receives a new observation and applies the previously learned transformation and prediction logic. The model should not be retrained for every request. The serving application loads the approved model and uses it repeatedly until a new version is intentionally deployed. A simple deployment has three major parts. The client application collects or receives the feature values. It sends those values to a REST API using an HTTP POST request and a JSON body. The Flask application validates the request, arranges the features in the expected order, and sends them to the saved model pipeline. The model returns a class prediction, and when supported class probabilities, the API converts the result into JSON and sends it back to the client. The client then presents the result to the user. REST stands for Representational State Transfer. In this chapter, the important idea is that an API provides a standard interface between applications. A desktop program, mobile application, website, or command line tool can send the same type of request to the service. The client does not need the model's training code. It needs the endpoint address, the required input fields, and the expected response format. This separation allows one model service to support multiple client platforms. The prediction endpoint accepts a POST request. POST is appropriate because the client sends a request body containing data to be processed. The body uses JSON, a text-based format built from keys and values. In this case, the keys identify glucose, BMI, and age. The API must verify that all required fields exist and contain valid numerical values. The order of keys in the incoming JSON should not be trusted as the feature order. The server should explicitly construct the model input in the order used during training. The book uses Flask to create the REST API. Flask is a lightweight Python web framework. A Flask application begins by importing the Flask class and creating an application object. Routes connect URL paths with Python functions. For this example, one route can provide a health check and another can accept prediction requests. Flask's local development server is appropriate for learning and testing. A real production deployment requires a production server and additional security and operational controls. The chapter demonstrates deployment through a diabetes prediction case study. The dataset contains medical diagnostic measurements collected from adult female patients of Pima Indian descent. The objective is to predict a binary outcome associated with diabetes. This example is useful for teaching data, preparation, classification, probability, and deployment. However, it must be treated as an educational demonstration only. A classroom model trained from a limited historical dataset is not a medical diagnostic system and must not be used to make healthcare decisions. The dataset contains several numerical medical measurements. These include pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pedigree function, and age. The target column is outcome. A value of 0 or 1 represents the recorded class. Before training, inspect the shape, data types, descriptive statistics, missing values, and class distribution. Do not begin by immediately fitting a model. Understanding the data is part of the machine learning workflow. Some columns contain zeros that do not represent realistic measurements. For example, a zero value for glucose, blood pressure, or BMI may indicate that the measurement is missing. Create a list of the affected columns and replace those zeros with NumPy none. Then inspect how many values are missing. The chapter removes incomplete rows using dropna in a real project. We would also investigate how much data is removed, whether the missingness follows a pattern, and whether imputation would be more appropriate. Cleaning decisions can change the population represented by the model. Before saving a model, we need evidence that its performance is acceptable for the educational objective. Cross-validation can compare candidate algorithms using repeated training and validation partitions. After selecting the approach and completing the evaluation, the approved pipeline can be fitted for deployment. The evaluation results and the final fitted artifact serve different purposes. Evaluation estimates performance. The fitted artifact is the object used for future inference. Do not report training accuracy as if it were an unbiased estimate of future performance. The chapter examines feature correlations using a correlation matrix and a heat map. Correlation summarizes linear association between numerical variables. In this dataset, glucose, BMI, and age are among the features with stronger relationships to the outcome column. Correlation does not prove causation. It also does not measure every possible nonlinear relationship. For the chapter's deployment demonstration, these three features create a smaller and easier to use input interface. Create the feature matrix using glucose, BMI, and age. Store the outcome column separately as why feature order matters. The client may send JSON keys in any order, but the server must construct the input in the same order used during training. We will preserve the feature name list and use it again inside the API. A stronger production design would also document units, acceptable ranges, missing value behavior, and the model version. The chapter compares 4 candidate algorithms instead of assuming one will perform best. The candidates are logistic regression, k-nearest neighbors, a support vector machine with a linear kernel, and a support vector machine with an RBF kernel. Each candidate is evaluated using 10-fold cross-validation. The same false and scoring approach should be used so the comparison is fair. Cross-validation produces multiple validation scores rather than depending on one favorable or unfavorable split. The mean and variability of those scores help support model selection. K-nearest neighbors and support vector machines are sensitive to feature scale. Place standard scalar and the classifier inside one Scikit-learn pipeline. The pipeline learns scaling parameters only from the training portion of each cross-validation fold. It also ensures that the same pre-processing is applied during future predictions. Saving the pipeline is safer than saving only the classifier because pre-processing and prediction remain together. The client sends original feature units. The pipeline performs the transformation internally. In the chapter's experiment, k-nearest neighbors with 19 neighbors produces the strongest average accuracy, reported at approximately 77.2%. The exact value may vary with data cleaning decisions, fault configuration, and software versions. The important lesson is the selection process. The model was not chosen because K and N is universally best. It was chosen because it performed strongest among the tested candidates under the chapter's evaluation setup. For another dataset, another algorithm may be more appropriate. After completing the evaluation and selecting the approach, create the final pipeline. The pipeline contains standard scalar followed by k-neighbors classifier with 19 neighbors fit the pipeline using the approved development data. This fitted pipeline is the object that will be saved and loaded by the API. Because preprocessing is included, the API can provide glucose, BMI, and age in their original units. The pipeline applies the same learned scaling before generating the prediction. The book saves its model using Python serialization. Here, we save the complete pipeline to the diabetes PyPlyPopKL, open the file in binary write mode, and use pickled up. This allows the API to load the fitted object without retraining it every time the server starts. However, pickle-based formats require an important security warning. Never load a model artifact from an untrusted or unverified source because loading can execute arbitrary code. Also record the Python and package versions used for training. Loading a model with a different Scikit-learn environment is not a supported deployment strategy. Organize the deployment example into separate files. Train-model.py contains data preparation, model evaluation, final fitting, and artifact creation. The pickle file contains the fitted pipeline. REST API by Py exposes the HTTP endpoints. Predict-diabetes.py is the simple client. A requirements file records the required packages and versions. The README explains how to build, run, and test the project. Separating training from serving makes the workflow easier to understand and maintain. The Flask service imports the application class, the request object, and JSON response support. Create the Flask application. When the service starts, open the trusted model artifact in binary read mode and load it. The model should be loaded once during application initialization rather than loaded again for every prediction request. If the file is missing, incompatible, or untrusted, the application should not continue silently. A production service should log the model version and fail in a controlled way. A health endpoint provides a simple way to confirm that the service is running. The root responds to a GET request at last health. It returns a small JSON object containing a status, model name, and version. A health check does not prove that every prediction is correct. It confirms that the application can receive requests and produce a response. More advanced systems may also verify dependencies and model loading. Create a post root at diabetes/v1/predict. The function begins by reading the JSON request body. Using silent to true allows the application to handle missing or malformed JSON and return a control error rather than an unhandled exception. The road path includes a version number. Versioning helps clients distinguish future API changes. The next step is to validate the payload before sending anything to the model. Never assume that a client sends complete or valid data. First, confirm that the payload is a JSON object. Define the required fields: glucose, BMI, and age. Create a list of fields that are missing. If any are absent, return a JSON error with HTTP status 400, meaning the request is invalid. A complete application should also convert values to numbers, reject values that cannot be converted, and apply reasonable range checks. Validation protects the model and gives the client a clear explanation of what must be corrected. Construct a one-row pandas data frame using the exact feature names used during training. Explicitly convert each value to a float. If conversion fails, return a control 400 response. Using a data frame preserves feature names and reduces the risk of accidentally reversing the input order. The model pipeline receives glucose, BMI, and age in the same structure used when it was fitted. This data contract should be documented for every client. Call predict to obtain the predicted class. The result is an array, so select the first value and convert it to a standard Python integer. Call predict cost prorat to obtain the estimated class proportions from the neighbors. Select the probability associated with the predicted class and convert it to a standard float. For k and n, this value reflects the weighted or unweighted vote among the neighbors. It should not be interpreted as a guaranteed medical probability. Return the result as JSON. Include the numerical prediction, a user-facing label, the rounded confidence value, and the model version. Also include an educational use disclaimer. Avoid presenting the output as a confirmed diagnosis. JSON uses standard serializable types, which is why NumPy values are converted to Python integers and floats. A consistent response schema makes the client easier to build and test. Start the Flask application from the command line. The app option identifies the module containing the Flask application by default. The development server listens on the local computer at port 5000. Keep this terminal running while testing the API. The built-in Flask server is intended for development and learning. Do not expose it directly as a production service. Production deployment requires an appropriate server, secure configuration, and operational controls. Before sending prediction data, test the health endpoint. Use curl with a local health URL. The response should confirm that the status is OK and identify the model version. If this request fails, verify that the Flask server is running, that the port is correct, and that the route matches the application code. Testing one layer at a time makes troubleshooting easier. Now test the prediction endpoint. The next post option selects the post method. The content type header tells the server that the body contains JSON. The next D option provides the glucose, BMI, and age values. The API validates the request, constructs the data frame, invokes the model pipeline, and returns JSON. Testing with Coral confirms that the service works before we introduce a separate client application. Also test missing fields and invalid text values to confirm that the error responses behave correctly. The client imports the request library and stores the prediction endpoint URL. It prompts the user for glucose, BMI, and age. The values are converted to floats and placed into a Python dictionary. Passing the dictionary with a JSON argument causes requests to serialize it and set the appropriate content type. The timeout prevents the client from waiting indefinitely if the service does not respond. The client knows nothing about standard scalar or KNN. Those details remain inside the deployed pipeline. Call raise for status, so unsuccessful HTTP responses are treated as errors. For a successful response, parse the JSON and display the label and formatted confidence value. Use exception handling for network errors, timeouts, invalid responses, and server-side failures. A client should not crash without explanation when the API is unavailable. It should provide a clear message and avoid presenting incomplete output as a valid prediction. The local Flask demonstration teaches the request and response workflow, but it is not a complete production architecture. A real service may require authentication, authorization, HTTPS, formal input schemas, range validation, and rate limiting. The model artifact must be stored securely and loaded only from a trusted source. The service should run behind the production server rather than the Flask development server. Logging should protect sensitive information. Monitoring should track availability, errors, model versions, and changes in incoming data. Teams also need a rollback plan and a process for reviewing model performance and drift. For high-impact decisions, human oversight remains essential. Let's connect the chapter into one complete deployment workflow. Begin by defining the prediction problem and documenting the required input features, units, and expected response. Inspect and clean the data before evaluating candidate algorithms. Keep pre-processing and the classifier together inside the pipeline so the same transformations are used during evaluation and inference. After selecting the approved approach, fit the final pipeline and save it as a trusted version artifact. The Flask service loads that artifact when the application starts. Each prediction request must be validated before its values are arranged in the model's expected feature order. The API returns a structured JSON response that the client can interpret. Finally, test successful and unsuccessful requests, monitor the service, protect sensitive data, and review whether the model remains appropriate for its intended use. Let's summarize Chapter 12. Model deployment makes a trained model accessible to another application. Training uses historical data to learn model behavior, while inference applies that learned behavior to new observations. A REST API provides a standard interface that can be used by command line tools, desktop applications, mobile applications, and web clients. The client sends feature values in a POST request, commonly using JSON. The server validates the request and constructs the model input using the correct feature names and order. A saved Scikit-learn pipeline keeps preprocessing and prediction together. Model artifacts must come from trusted sources, and the training and serving environments must remain compatible. A classroom Flask demonstration is useful for learning, but a production deployment also requires security, monitoring, privacy controls, versioning, rollback planning, and human oversight. Deployment makes predictions available. It does not remove the need to understand the data, evaluate the model, communicate limitations, and interpret results responsibly. This concludes Chapter 12 and our lecture on deploying machine learning models.